Welcome, everyone. I am pleased to present the architecture for our neural text-to-speech system. Our primary objective was to implement high-fidelity, offline speech capabilities by leveraging the performance and safety of Rust and the Tauri framework. As indicated, we successfully completed the implementation phase on January 30th, 2026. The foundation of the system is built upon three core technologies: the Piper Neural Engine for high-quality voice synthesis, the Onyx runtime for optimized cross-platform inference, and Rodeo Audio for seamless low-level audio playback. This integrated stack allows us to deliver a responsive and private user experience by processing all speech synthesis locally on the device, without the need for an external cloud connection. Let's take a closer look at how these components interact to produce such clear, natural results. The objective for our Listen to Article feature was to create a seamless reading experience defined by strict technical boundaries rather than just feature additions. To achieve this, we established 5 core requirements. First, we focused on high fidelity, requiring neural voices because standard robotic system voices were insufficient for a natural experience. Second, the solution had to be strictly offline to eliminate cloud dependencies, prevent privacy leaks, and avoid per-character costs. Third, we prioritized a cross-platform approach to ensure identical behavior across macOS, Windows, and Linux. Performance was equally vital, with a low-latency target requiring audio start times to stay under 2 seconds. Finally, we implemented streaming capabilities so that playback could begin immediately while the voice generation continues in the background. To understand why we arrived at our current solution, we must first examine the graveyard of attempts, the standard approaches that failed to meet our specific engineering constraints. We initially considered native browser TTS, but rejected it due to its robotic audio quality and lack of consistency across different operating systems. Cloud APIs, such as 11 Labs, were also ruled out because they violated our non-negotiable offline requirement while introducing significant privacy concerns and high operating costs. Our most significant setback was Kokoro.js, which resulted in a critical failure. It suffered from WASM timeouts within web views and experienced unacceptable latencies exceeding 120 seconds on macOS. Finally, XTTS v2 was rejected due to its impractical footprint, as a 1.5 gigabyte download size was simply too large for our deployment model. Each of these failures helped refine the strict boundaries for the final architecture. Our solution utilizes the combination of Piper and ONNX runtime to strike a pragmatic Goldilocks balance between fidelity and footprint. By optimizing for native ONNX, we achieve highly efficient inference with a remarkably small footprint of only about 63 megabytes, a massive reduction compared to the 1.5 gigabytes required by alternatives like XTTS. On the other side of the scale, we maintain impressive quality, delivering a mean opinion score of 3.6, which provides near Siri fidelity. Perhaps most importantly, this system is designed for CPU-only compute, meaning it requires no GPU to function effectively. This makes it an ideal choice for high-performance voice applications where hardware resources are limited. This architecture diagram outlines the flow of our text-to-speech system, bridging a TypeScript front-end with a Rust-based back-end. In the front end, the TTS UI.ts module provides a unified interface, which interacts with TTS Neural.ts to initiate requests. These requests cross the bridge to the backend via Tauri IPC. Within the backend's dedicated TTS module, the coordinator handles the primary logic and directs tasks to the engine, where Piper and the ONNX runtime perform the actual synthesis. The final audio output is managed for playback by the Rodeo library. To ensure constant availability, the system includes a fallback safety net that defaults to the native OS text-to-speech capabilities if the primary neural engine cannot be reached. The inference pipeline illustrates the journey from raw text to a final WAV audio file through 6 distinct stages. It begins with text input, where article extraction isolates the relevant content. This is followed by pre-processing, which involves URL removal and normalization to prepare the data for analysis. In the third stage, phonimation, the text is converted into the International Phonetic Alphabet using eSpeak-NG. As shown in the example, a word like hello is translated into its phonetic equivalent. Moving to stage 4, ID mapping, these phonetic representations are mapped to a JSON configuration, turning them into numerical inputs. The core of the system is the inference stage, where the ONNX runtime processes these tensors through a neural network. Finally, the pipeline concludes with audio output, where the Radio V021 library streams the resulting audio data, delivering the final synthesized speech. Managing user experience friction is critical when handling significant asset downloads, such as this 63-megabyte neural model. During the first run, the Read Neural button is styled with a dashed border to indicate that a download is required. Interacting with this button immediately triggers a size warning dialog, providing transparency regarding data consumption before any transfer begins. Once the process starts, the downloading phase utilizes a blue info toast with a progress bar to keep the user informed. Crucially, native text-to-speech remains available as a fallback, ensuring the core functionality is not blocked while the enhanced model is being retrieved. In the event of a failure, such as a network timeout, we transition to an error state, represented by a red error toast. This notification is designed to prevent duplicate alerts, maintaining a clean interface even when connectivity issues persist. These steps collectively ensure a graceful and predictable experience for the user. The synchronization challenge highlights a common friction point when consuming audio content: the lack of visual orientation. Even when the audio quality is excellent, users often struggle because there is no visual anchor to guide them. This makes it difficult to resume listening if they are interrupted, and frequently leads to users getting lost, especially in longer articles. Our goal to address these issues is to implement precise, sentence-level highlighting. By providing a clear visual indicator that moves in lockstep with the audio, we can ensure that the user always knows exactly where they are, creating a more seamless and engaging experience. When evaluating our synchronization strategy, we faced an architectural fork between timer-based estimation and an event-driven model. Option A involved calculating playback duration based on word counts. We rejected this approach because it inevitably leads to drift accumulation and fails to maintain synchronization during pause and resume actions. Instead, we selected option B, an event-driven architecture, where the backend emits a signal every time audio is pushed. This ensures perfect synchronization, zero drift, and native support for pausing. The primary trade-off for this precision is a higher volume of IPC traffic, which we determined was a necessary cost for a seamless user experience. The event loop is the central mechanism we use to orchestrate precise synchronization between speech and the user interface. The process begins when the front-end requests speech by passing a text array. From there, the back-end generates the current sentence and begins audio playback, simultaneously emitting a start event. To account for processing overhead, we include a latency compensation of 50 milliseconds added after the sync append function. This ensures the visual highlights remain perfectly aligned with the spoken word. When the front-end receives that start event, it highlights the corresponding UI element in cyan. Finally, once the backend finishes the segment, it emits an end event, signaling the system to move to the next sentence and begin the cycle again. The invisible normalization bug represents a common challenge when integrating text-to-speech engines with web content, specifically regarding whitespace drift. As illustrated in the diagram, a raw HTML DOM often contains significant whitespace, such as new lines and tabs, used for code legibility. This slide outlines the pacing and chunking strategy used to optimize text readability. A common problem occurs when raw sentences are displayed individually. Very short phrases like "I agree" or "yes" flash on the screen too quickly for a viewer to process comfortably. To solve this, we implement chunking. By grouping short pieces of text into a combined block, targeting a minimum of 200 characters, we create a more stable reading experience that allows the brain to settle into the content. Our automated workflow manages this balance through a specific logic path. When raw sentences are processed, we evaluate their length. If the text is under 200 characters, we merge it with adjacent content to provide more substance. Conversely, if a segment is too long, exceeding 400 characters, we split it to prevent overwhelming the reader. This systematic approach ensures a natural reading rhythm that is neither too fast nor too dense. The visual experience is designed to be both functional and unobtrusive. A sticky header at the top keeps the user oriented by displaying the current sentence progress, such as sentence 3 of 15, using the Inter and JetBrains mono typefaces. The system automatically identifies the active sentence, highlighting it and auto-scrolling to ensure it remains centered in the view. Crucially, we maintain the original DOM structure through the use of temporary span wrappers, allowing for precise interaction and styling while preserving the integrity of the document's underlying layout. Turning to our current implementation status, we have successfully met all key milestones for the version 1.0 release. Our neural pipeline, utilizing Piper and Onyx, is now fully functional in an offline capacity. The audio system has been solidified with a stable Rodeo 0.21 integration. We have also perfected our synchronization through event-driven highlighting, achieving impressive sub-sentence accuracy. In terms of reliability, our codebase is robust, with 91 Rust tests and over 1,000 TypeScript tests currently passing. Finally, we have integrated fallback logic to ensure a seamless degradation to native TTS whenever necessary. With these components in place, version 1.0 is officially live. Looking ahead at our future roadmap, we have several key milestones designed to enhance the platform's performance and accessibility. First, we are focusing on GPU acceleration by implementing CUDA and CoreML to achieve instant generation with a performance target of over 1.0x real-time. Next, we will introduce voice cloning to provide users with advanced customization options. We are also developing a click-to-jump feature, which will streamline navigation by allowing users to jump to specific sections simply by clicking on text blocks. Finally, we will expand our capabilities with multi-language support, integrating non-English models via Piper. These initiatives are all focused on our core mission, delivering a seamless, privacy-first reading experience built on the reliability of Rust.